we had our little part 2 of our test to complete for was due this weekend, and we did that. I noticed most of us, 90% of us did it anyways. Thank you. And the scores weren't quite as great as I would like, and I apologize. I mean, I'm not blaming you, I'm blaming myself. I didn't think they were, I thought they would be a little bit better. They wasn't like they were horrible. The average was 75% right, which I think that's the middle of a C, I know, but I would kind of hope they would have been a little higher. So what I did was I added 5 points to everybody's score. If you go out to Moodle now and you look at it, whatever you got when you took it should be enhanced by 5 points. And I'm got some more things that we can do on magnetism and such, but I thought maybe I'd wait a day or two because we're probably don't really want to go right back to it yet. I'll wait a day or two and put some more things out there that we can do and complete our second unit, I guess, would be what we will say we were doing. Now what we are delving into is how humans have, over the past 150 years or so, used electricity as a means to store energy and harvest energy and convert it into our usable forms of energy. It really boils down to the fact that we really want motion. That's what we want to use energy for, to gain motion. And when that motion is me moving my arm up and down, I am able to do that by eating a hamburger. And the hamburger is converted actually into electricity in me. And then the nerve endings tell my muscles to bend and contract to make me capable of moving my arm. Sort of the same thing in a car. I put some dinosaur goo into the engine of my car, and when I turn my car on, I'm breaking a bunch of chemical bonds in the dinosaur goo, and it's converted through the wizardry of engineering into pushing my car down the road. Well, what we have found over the past 150 years is a very efficient means of storing energy and then later taking it out of the bank and using it to make motion is electricity. It's a wonderful source of energy storage that we can take advantage of. Now, you might claim, well, we don't only need electricity to make energy of motion, we need it to make the energy of light as well, because we don't like to sit around in the dark, so we do it for that purpose as well. And we might say we do it to heat. Well, I would claim in that regard, heat is motion. It's just a different manifestation of how objects are moving. The hotter they get, they're just moving more and more dramatically. It's just that they're moving randomly when you heat an object up. And so the hotter you make something, if you could look at it closely, you would see that it is just moving much more dramatically the hotter it gets. So we are wishing to make this energy of motion and maybe some energy of light that can help facilitate and better our lives. And one way to do that is to do chemistry, burn materials, which was the way that we typically generated these motions of this motion energy for quite some time in human existence. But over the past 150 years, by far and away, the way that has gained the most popularity to store the energy and later harness it is through the electrical means. Now, ultimately, what we're looking at here at first, to make electricity, again, we're going to turn to chemistry. So we're doing a chemical trick in order to make electricity occur. And the chemical trick was pioneered by an Italian by the name of Galvani. He really happened upon this phenomenon, didn't really seek it out, but was actually working as a biologist on the anatomy of frogs when he noticed, as I talked about on Wednesday, that when he touched his scalpel on a freshly killed frog's nerve endings in their leg, the leg kicked as if the frog was still alive. And what was eventually realized was that the metal in the scalpel was losing electrons into the neurons of the frog's legs and completing the circuit that was telling the muscle to contract, as if the brain was sending the same electrical impulse. So after much time of fooling around, Galvani and his compatriots in Italy, including a guy by the name of Volta, which should be a name that makes sense when you start to think about common terms in electric technology. Well, they perfected the ability to use chemical reactions to generate electricity. Now, again, they did this in the very beginning of the 1800s. And since that time, which of course, some 220 years later, we have really invested a lot of time and a lot of money and a lot of technology in honing and improving the technique of battery design, battery ability, the amount of energy that can be contained in batteries, the length that they last, the rechargeability of them, of course, is an absolutely critical factor. I would just like you to think of how many times you recharge your cell phone battery. It's pretty remarkable, really, when you stop to think about it, how durable and how reliable it is. I mean, sometimes we get a little upset about it because of it seems to not do everything that we so desire. But when you really stop and think about the technology that went into it, it's really simply quite remarkable. So all of this really, if you look closely at what's going on, every time you power up your cell phone, you would see that at the root of what is occurring to make it possible for you to slide across through your contacts is that there's a chemical reaction generating electricity that powers the LEDs and such in the screen of your smartphone. So what we're going to do then is go to my slides, of course, and we're going to explore some slides. Now, again, some of the things on these slides might not be exactly everybody here's cup of tea, but I'm trying to give you a sense of how the chemistry connects to the science of the battery. And I'm going to throw some anecdotes in while we're going through that about how batteries are, what important properties batteries must possess to make them usable and better for everyday applications. Okay, so I'm going to hit my buttons here, of course. Let's say I want to present. I'm going to do all that good stuff. I'm going to click on the thing and hit share and all that good stuff. And then hopefully we are going to pop my slides up. Now this, I believe, is where I did end up on Wednesday of last week. I was talking about this individual, Galvani, who I said pioneered the idea of the so-called chemical storage battery. Now, what we mean by that is he's storing energy from chemical reactions that we can transmit into moving charge. And it shouldn't really be surprising that charge in motion occurs when you have chemical reactions. And I'm going to back up maybe a slide or two. Ooh, no, I don't. I guess I want to go forward a slide or two. Sorry, going the wrong way here. I wanted to go to this slide. In particular, I have a piece of zinc here that when I place in a solution, and we talked about what a solution means, homogeneous mixture of a material known as copper sulfate with water, and the homogeneity means that the copper sulfates are distributed evenly through an inundating number of water molecules. So really there's a relatively small amount of the copper sulfate compared to the huge, vast amount of water. So if I stick a piece of zinc in there and leave it for a few minutes and pull it out, I will notice that the zinc is altered. And what has ultimately happened is that I have, as we would call it in chemistry, electroplated the zinc with copper. There's a copper coating covering the zinc now as a result of me putting that strip of zinc down there. This is a spontaneous process. Spontaneous in chemistry means happens without me providing energy to induce or entice it to happen. It happens naturally. No need to kick it in the butt to make it occur. Now, interestingly, if I did something that you would consider the exact opposite of this, it wouldn't be spontaneous. For instance, if I, instead of taking a piece of zinc, I took a strip of copper, and instead of putting that strip into a solution of copper sulfate, I put it down into a solution of zinc sulfate. So if I put a strip of copper into a solution of zinc sulfate and pulled the copper out after some time, there would be no reaction. Turns out that these things happen in one direction spontaneously, and in the other direction, they are what we would consider to be non-spontaneous. Now, having said that, what I would point out to you, if I entice the reaction to go that is non-spontaneous, it will go. Now, what does that mean to entice it? I must supply energy to force that reaction to go. So again, if I put a piece of copper down into a solution of zinc sulfate, the only way there will be a reaction is if I supply energy, actually in the form of electricity, that I feed through the copper, through the copper so that it gets into the zinc solution. Then that would go with my inducing it. But spontaneously, a piece of zinc placed in solution of copper sulfate makes a reaction go where copper sticks onto the zinc electrode. Now, I then talk to you about what a chemist would write to represent this process. The equation on the top of this slide is showing how zinc reacts with copper sulfate. Those are the so-called reactants. They're the materials on the left. And after they react, they form products, or a chemical change has occurred. The zinc has been altered and the copper has been altered during the course of the chemical process. And what a chemist would probably call this is a single replacement. The zinc kicks the copper out of the compound and takes its place, while now the copper is elemental. Now, it turns out that both zinc and copper sulfate are electrolytes. And what it means to be an electrolyte, and this is the same thing that it means in a Gatorade bottle, is that you exist as charges in the solution. So really, instead of just being a molecular copper sulfate, the copper sulfate is a collection of charged cations and charged anions. Instead of being a neutral zinc sulfate in solution, the zinc sulfate is charged zinc cations and sulfate anions in water. Now, when water is not there, the zinc sulfate and copper sulfate are molecular. They're stuck together and they are net neutral. It's really the action of water itself which forces this occurrence of electrolytes to not only dissolve, meaning disappear and hide among the water molecules, they, as we call it, ionize, break into charges in the solution. And those charges are now free roaming, positive and negative. Now, what chemists like to do is to cancel, treat the arrow like an equal sign. And on both sides of the arrow, there are common values. And those common values on both sides of the arrow are sulfates, what we call them, SO4s. Notice there's an SO4 minus 2 on the left there's an SO4 minus 2 on the right. So just like you would do if this was an algebra class, is you would cancel the SO4 minus 2 on the left and cancel the SO4 minus 2 on the right. And after you do that, and unfortunately, it's kind of hiding behind my share button, but it shows you the actual spontaneous electron transfer, as this slide is named. What it says after you eliminate the sulfate and don't consider it is that neutral zinc finds a copper that is a cation, and now when they're done doing that, they find each other. The zinc is now a cation and the copper is neutral. So there is electron transfer. The zinc starts neutral and becomes cation plus 2. The copper starts as cation plus 2, and when it's finished becomes neutral. How can the zinc go from neutral to positively charged? It does so by losing electrons. How does the copper go from plus 2 charged to neutral? It does so by gaining electrons. So this is what we call electron transfer between the zinc and the copper. The zinc loses electrons and the copper gains electrons. Guess what that constitutes? Transfer of electrons, if done through a conductor, is electricity. So we have essentially done an electrical reaction between the zinc and the copper. And as we said on the previous slide, this is spontaneous, meaning it occurs naturally. You don't have to do anything to make this happen. So essentially what we're then saying is electricity spontaneously flows between zinc and copper. Now, what you can do then is separate zinc from copper in your cell phone. In between the zinc and the copper, you put your screen and your buttons and your whatever you want to do, some transistors and some other cool little electrical devices that people have figured out how to develop over the last 100 years. And now you make an electrical circuit from the chemical spontaneous transfer of electrons from zinc to copper. So we're going to explore that on the next couple of slides. Zinc is undergoing what we call oxidation. Oxidation is losing electrons. So again, let me back up and look at the bottom equation that's kind of covered up. I have zinc neutral on the left, zinc plus 2 on the right. And how does it go from zinc neutral to zinc plus 2? The zinc loses electrons, which I'm representing as E minus. Now to go from zinc to zinc plus 1, it would have to lose 1 electron. To go from zinc to zinc plus 2, it has to lose 2 electrons. Now, if it was going from zinc to zinc plus 3, guess what? It would be losing 3 electrons. Now remember, as we talked about previously, when something becomes positively charged, it doesn't do so by gaining protons. That would mean all kinds of crazy energetics trying to jam positive charge into a nucleus. To positively charge any entity in our world that we typically deal with, you remove electrons to make positive charge. So the zinc has electrons removed from it and becomes a cation, as that equation shows. Simultaneously, meaning at the exact same instance, of course, any copper cation that is near the zinc is absorbing these electrons. Now, let's recall something that was stated by Ben Franklin earlier on in our discussion. That is that the universe conserves charge. It is not created or destroyed. So if zinc is naturally producing electrons in this spontaneous process, we're not building up excess electrons in the universe. Simultaneous to the zinc losing electrons, you must have copper gaining electrons. This is one reason that we will later see, and this is something I think that makes sense to you, that an electrical circuit has two terminals. There are terminals in a chemical reaction, or I'm sorry, in an electrical reaction. The terminals are where we have loss and gain of electrons. So every battery has two terminals. At one of the terminals, electrons are being lost. At one of the terminals, electrons are being gained. And you will note this when you stick batteries into your devices, because typically there's little marks that say plus or minus. Now, typically, the butt end of the battery is where the electrons are lost. Typically, the little nubby thing sticking up is where the electrons are gained. Typically. Now, can you design batteries to be opposite of that? Yes. But they're all kind of designed based on industry standards so that you could use Rayovac batteries with Eveready batteries, with Duracell batteries, and they will all at least appear and operate and function in the same way. So it makes sense that the industry would have a standard as to how these things should operate. Now, again, I will point out it doesn't have to do it that way. It's just that that's the way they have chosen to do it. So there's compatibility between brands. Okay, so the copper simultaneous to the zinc losing electrons, the copper gains electrons. In chemistry, we call gaining electrons reduction. Now, what can you think of reduction as meaning? Reduction has the connotation that the charge that you see is being reduced. If you have a charge of +2 and you gain 1 electron, you're now +1. So that's where the reduction idea comes from. If you have a charge of +3 and you gain 2 electrons, you reduce your charge to +1. So that's where and how you can think of what this name means. Gaining electrons, as weird as it sounds, is what a chemist calls reduction. That sounds counterintuitive, I agree. Gaining electrons, reduction. Those two words don't normally go together in a sentence, but that's what they mean. And typically what the point would be is that the charge is lowering. So you're reducing the charge. Now then, why is what zinc is doing called oxidation? It's not reacting with oxygen. So why is losing electrons in chemistry called oxidation? Well, it's a traditional thing because of giving, if you like, giving respect to oxygen. It turns out that oxygen is the most reactive thing in our environment. Now, it's not actually the most reactive thing on Earth, but it's so prolific, meaning there is so much oxygen, and it is very reactive, that because of this prowess of oxygen as a powerful reactor, that we name this process of losing electrons oxidation. Now, it turns out the premise of or the power of oxygen is in its ability to gain electrons. So when materials lose electrons in nature, 9 times out of 10, a material losing electrons in nature is losing electrons to oxygen. So that's where the origin of this name comes from. Generally, when you're losing electrons, you are doing it to oxygen. In this particular case, you're not, but we still call the zinc losing electrons oxidation in the sense that things generally lose electrons, they're losing them to oxygen. Like, for instance, when iron rusts, when it goes from metallic iron and becomes that orange powdery stuff that we've all seen here or there, rust is iron losing electrons to oxygen. Rust is the oxidation of iron. And I guess that kind of makes sense That's what that would be. But in this case, zinc is being oxidized, but there's no oxygen in the process at all. I apologize for that. I didn't make the terminology up. I'm just trying to tell you the origin of the terminology. So again, losing electrons is oxidation. It is named that in deference to oxygen as being a powerful reactor in everything that we do. You and I are running on oxidation constantly. Again, if you ate some cereal this morning, it's being burned up in your stomach and converted into fuel that can make it possible for your heart to beat and pump your blood and think even through your neurons. And all these things are occurring ultimately through reactions with oxygen present, and materials are losing electrons to the O2 that you're breathing into your lungs in order to pull these things off ultimately. Okay, so we have oxidation and reduction reactions. Now, as I have already mentioned, and as it says at the bottom, spontaneously the zinc will lose and the copper will gain. The opposite is not spontaneous. So when you put a battery into your device, and as I mentioned last time, the major way in which we've made batteries for centuries is using copper and zinc. Now, ultimately, as we will see, there are other kinds, but copper and zinc are the #1 source of commercial battery terminals. In every copper and zinc battery, the zinc is losing electrons, the copper is gaining electrons. If you separate these processes by conducting wires, you can flow the charge through the circuit. So in every battery that we see, we have this ongoing chemical process where zinc is losing electrons, copper gaining them, and we harvest the electricity. Well, guess what? They don't go on forever because they're going to run out of fuel, as we see. Now, the reverse is not spontaneous. The reverse is not spontaneous. Copper will never lose electrons to zinc. Only zinc will lose electrons to copper. So what happens when you burn up all the zinc? Well, we'll talk about that upcoming here. Okay, so that was kind of a backup there. Let's go on to the idea of separating the oxidation from the reaction, from the reduction. So this is kind of what a battery does, but it doesn't do it with jars and chunks of metal like you're seeing here. But this is how a chemist would mimic what a battery is doing for you. I have separated the copper from the zinc and connected them with a conductor. Notice now on the left, I'm showing the original reaction. I put a piece of zinc down into copper sulfate. On the right, what I'm now saying is let's separate the two processes to harvest, the electrical power. So I put the copper stuff all on the left. I put the zinc stuff all on the right. Now, when I connect them, spontaneously, electrons begin to flow. Charge moves from the zinc to the copper. Now, if I do not connect the zinc terminal to the copper terminal, then there will be no flow of charge. Air is an insulator. There's not enough electromotive force for electrons to naturally transfer unless a good conductor is connected between the two. So I have a spontaneous flow of charge, and I can plug in there a light bulb. And then the light bulb can be lit up by the flow of charge through it, just like you do in any flashlight. Okay, so these are called galvanic cells in deference to Luigi Galvani, who figured these things out in the 1700s in Italy. And what we can do is break it down at each terminal into the reaction that is going on. We can take it a step further. We can measure the electrical output that these processes would give. So what I'm showing on this slide is I have my two terminals of the battery, the copper terminal and the zinc terminal, and some chemist somewhere has measured what does the V symbol mean? It means what kind of voltage, and what voltage turns out to mean, and I'm sure your mom and them have heard the term voltage. What voltage means is the electrical energy stored or provided to power the process. So somebody has been able to measure the voltage it takes for the copper to gain electrons and the zinc to gain electrons. Now, what I want you to notice there is that one of these E values, which is the voltage, is what chemists give for it stands for electromotive force, which says something about the electrical energy required or given off in this process. It's really not so important, but that's what the E stands for to a chemist. When somebody measures this, they would find on the copper side, as copper ions gain electrons, you get 0.34 volts. Plus signs mean this is what you harvest. So you can harvest plus 0.34 volts every time you have a copper atom gain 2 electrons to make a charged copper atom gain 2 electrons to make a neutral copper atom. You get given off in that process 0.34 volts. Now on the right, I'm showing zinc gaining electrons to become neutral zincs. You will notice there's also a measured value. Some chemist somewhere did this. But the most striking thing you notice, it's a way bigger number, but more importantly, it's a negative number. Now, the implication of a negative number is that this is not how much how much energy is given off. When the number is negative to a chemist, what it turns out to mean is that this is the energy you must supply. So what we're saying on the right is if I wanted zinc to gain electrons, I'd have to put energy in. How could I do that? Plug the zinc terminal into the wall. Then I can force it to gain electrons. If I want it to run spontaneously, it won't. Why? The negative voltage means I must supply that many volts to make the zinc gain the electrons. Well, if you will look closely at what I'm showing, this isn't good anyways, because my battery is not set up for one terminal to lose and one terminal to gain. The way my battery is set up here, both terminals are gaining. That's what the equations underneath the terminals are saying. The copper plus 2 is gaining 2 electrons. The zinc plus 2 is gaining 2 electrons. So in actuality, what happens is that you reverse what the copper does and you reverse the sign of the reaction. So this is the spontaneous process occurring on the right. Notice, compare the equation on the right to the left. On the right equation, I have the neutral zinc becoming a cation, but on the left equation, I have the cation copper becoming the neutral copper. This is how a battery must function. One loser, one gainer. Now notice the other important thing. both of these voltages are positive. When zinc becomes zinc plus 2, 0.76 volts is given off that I can harvest. When copper plus 2 becomes elemental copper, plus 0.34 volts is given off. I can harvest. So if I now have a spontaneous flow, I can call the two terminals the cathode and the anode. So that's what chemists and physicists, for that matter, refer to these pieces of metal as. First of all, we call them both terminals. They're kind of like the end point of the reaction. But the terminal where the electrons are lost or where oxidation occurs, that's an anode. The terminal where electrons are gained, the piece of metal where the electrons are gathered together, is called the cathode. So reduction occurs at the cathode, oxidation occurs at the anode. Now, if you were to put a voltmeter on this reaction, and that's what I'm doing on this slide, it wouldn't read 0.76, it wouldn't read 0.34, it would read the total output. And the total output of this battery cell, so this is called a cell. This would be what would be contained in one single thing that you hook into a circuit. The output in this cell would be 1.1 volts. Now, the industry, of course, has standards, and I'm sure you probably know what the standard is. They adjust the amount of the zinc, they adjust the amount of the copper, and then by changing the concentration in the cell, you can change those numbers. The industry standard for a battery that you buy, of course, I think probably about all of us know it, it's 1.5 volts. So how did I only get 1.1 volt here? I neglected to mention that there's a certain concentration of the copper sulfate dissolved in the solution. There's a certain concentration of the zinc sulfate dissolved in the solution. Those are what lead to the numbers that I'm giving for the voltage that I get. If I increase the concentration of the copper in the solution and the zinc in the solution, I can increase the output voltage. So that's what is done by industry standard. And again, the industry standard is that each battery should give out 1.5 volts. Now, let's be careful. Those are for A, or AA, AAA, C's, and D's. AA, AAA, C, and D give off 1.5 volts. The little square ones, all right, we've all seen them. They got kind of weird tips on them. They have the terminals both on the top. One's like a little pointy one, and one's like a little, you can stick something into it, one's you stick into something else. And those little square ones are 9-volt batteries, of course, we know. So by industry standard, they make 9 volts. A car battery makes 12 volts. Okay, so your typical diehard or whatever car battery runs your car, that is a 12-volt output battery. And I think I might show some examples of that coming up here a little later. So you can adjust the concentration of the electrolytes. By adjusting the concentration of electrolytes, you can tune in certain voltages. And then by industry standard, A or AA, AAA, CD, they're 1.5. Now then, why do we have to have AA, AAAs? Why don't they just have one? Well, there's going to be a lot of difference in the storage capacity or length of time which they will work. Now, there's other considerations as well too. There's a balance between the voltage and the current. The more current you want or need, the quicker you're going to drain the voltage. So if you're trying to run an electric drill, or for that matter, an electric lawnmower, which they now routinely make, these are going to draw, as we say, a lot more current. So you will be using up your voltage. The current you use is proportional to the voltage you draw off the battery. So if you want to double the current, you're going to draw double the voltage out of it. If you only need 1/10 the current, it will only take 1/10 the voltage to supply that current. So what the difference then in the D compared to the C compared to the AA or AAA is, again, how long it can supply a certain current. So this is why they just have different sizes of batteries, even though their output voltages are the same, so that they can feed that voltage, or dependent on the amount of time they can feed that voltage is a lot to do with it. Okay. There's something else weird about this battery that I want to point out. Notice that the cathode, where the copper is reacting, the copper's on the cathode, the zinc is on the anode. The cathode is coming apart. Oh, I'm sorry, I'm wrong on that. Notice the reaction that's happening at the cathode. At the cathode, the copper, is coming out of the solution, and I'm making excess solid copper compared to when it starts. Now let's look at the reaction that's occurring on the right. That's the terminal I called the anode. The anode is where zinc is becoming zinc plus 2. So the point would be, if you weighed the zinc terminal, then you plug the battery in and you let it run for a while. Then you weighed the zinc terminal again. Guess what? It's going to weigh less. Why? Because after you have run the battery for a while, zinc is becoming aqueous zinc plus 2, or it's piling up in the solution. So the zinc terminal will weigh less after some period of time. Conversely, on the other side, if I start the reaction, or before I start running my battery, I weigh the copper terminal. Then I let the battery run for a while. The copper terminal will weigh more. Why? Because the solution, which had copper plus 2 in it, is now making solid copper. It doesn't float around in the solution. It sticks on the terminal. So during the course of using this battery, the cathode's going to get heavier. The anode's going to get lighter. So guess what else that means? Eventually, you're not going to be able to put out 1.5 volts anymore. After you use enough of the anode, it just doesn't have enough zinc left to continue to output the voltage you want. So your battery is eventually, as we all well know, going to run down. And as a matter of fact, I think we're all aware with our cell phone usage, we can only get a couple, depending on what we're doing with it, we can only really get a couple of really good hours of peak performance from the cell phone battery. Okay, now you should now stop for a moment and appreciate the industry of battery design. Think about the characteristics of batteries and some of the things that would be desirable characteristics for new battery design. One, of course, would be safety. I would have to say that has to be number one. It can't use lethal chemicals, or preferably it can't use things harmful to the environment. It's got to be things that we can carry around in our pocket without blowing up. Now, I think we're all very aware there was an issue recently with what were called lithium ion batteries. And what was happening with lithium ion batteries is they could be overcharged. And you could be carrying a lithium ion battery around in your pocket and bad things could happen. So you'll notice that much of the discussion about lithium ion batteries has kind of gone away. That's because the industry took steps to get rid of these troublesome batteries very, very quickly. Well, I would probably say more correctly, government regulation stepped in and said, you ain't using that no more. Now, of course, the industry was upset because they invested a lot of time developing it, and it worked really well. But, I mean, safety had to be the number one priority there. So, of course, that's probably priority number one. I would say then second priority is cost. Nobody wants, and I often do this myself. I go to Walmart and I pick up that pack of AAAs. I'm like, these Duracells are $12 for 8 AAAs. And then I say, the Rayovacs. The Rayovacs are $6 for 12 AAAs. But what happens when I put those Rayovacs into my thing? They last 1/2 as long, probably not even 1/2 as long. Sometimes they last 1/3 as long. So, of course, cost effectiveness now becomes another issue with the battery. Now, then, of course, there are other issues too, of course, like how long it can hold the charge, just so many things. And I can't overemphasize to you just how important the battery industry is. All the wonderful technology that you want at your avail and you want to be able to take advantage of. Think of how much batteries play a role in those devices. And if you haven't noticed, they're becoming more and more prevalent to drive cars. They make electric lawnmowers nowadays, electric weed whackers, all electric leaf blowers. All these sorts of things are becoming routine. There was a time when every drill that every carpenter used had to be electrically powered. I guarantee you there's not a carpenter in the country, professional carpenter in the country now, who doesn't use a battery-powered drill. That's absolutely a certainty. So the technology has gotten dramatically better, and the secret is the chemistry behind how to pull these batteries off. Okay, now then let's talk about the opposite process. Okay, this galvanic cell is spontaneous, meaning as soon as you throw it into your cell phone, it works. But as we pointed out now, there are problems with the terminals. The terminals are either losing ions in the juice or they're losing solid terminal metal as the chemistry happens to make the electricity. So what we do and what we have done over the past 50 years is developed electrolytic cells. Now, again, I want to point out that this has only been over the last 50 years where these have been really commonly employed. And what would your mom and them call an electrolytic cell? It's a rechargeable cell. Okay, now again, I will point out to you, when I was a kid, we had batteries, mostly those silver Everetys, mostly D, but they would last 4 or 5 hours and be done. And you just threw them away and you had to buy more. Think if you had to replace your cell phone battery, throw it away and buy a new one every time you needed to recharge your phone. That wouldn't work. So the electrolytic cell has been a major emphasis of development in battery technology for the past 50 years. So electrolytic cells mean they're non-spontaneous. And what does it mean? When they're non-spontaneous, they flow in reverse. So you have to supply energy to run them backwards. So if I run the copper zinc battery in reverse, notice, and you might not recognize this, but everything is backwards on this diagram. The direction that the electrons are flowing is backwards. The reaction occurring at each terminal is backwards, meaning on the galvanic cell, copper plus 2 was gaining 2 electrons and becoming elemental copper. On the galvanic cell, zinc was losing 2 electrons and becoming zinc plus 2. That was the spontaneous process. Now in the electrolytic process, copper is becoming copper plus 2. Zinc plus 2 is becoming zinc. What does this mean? The zinc metal is being replaced. I'm replenishing the zinc terminal. The copper plus 2 in the juice is being replaced. Now, again, I'm just going to back up real quick to the slide before. This is the spontaneous way. Notice in the spontaneous way, the zinc terminal is losing metal. Notice in the spontaneous way, the copper in the juice, in the beaker, is becoming solid copper. So now when I go to the spontaneous way, the copper metal is making more copper ions. The zinc in the juice is making more solid zinc. So when I run the battery in reverse, I'm replenishing the diminishing quantities. So what cost is that? What do I have to pay for that? It costs energy. I must supply energy to run the electrolytic cell. What does that mean to you and me? I plug in my phone. When I plug in my phone, literally, I'm running the battery in reverse. I am running the battery in reverse to replenish the losing materials. Now, I also then want you to stop and think. Think, how many times you recharge your battery? There's 365 days a year. I'm going to bet 360 times you recharge it. Maybe not. Probably. Maybe even more. Maybe you charge your battery more than once a day. I don't know. See, I'm pretty, I charge mine about every other day because I don't really do a whole bunch with it, but I know how much other people use their phones and I know how much they charge their phones. So as you can imagine, once again, the technology behind batteries has played such an important role that now rechargeable batteries are second nature, or they're almost indispensable. In so many applications, rechargeable batteries are absolutely positively required in order to make the technology feasible. It wouldn't be worth it. Just think if you had to go to the store and buy a battery every time. Do you really think, how long do you think you would be using that cell phone if you had to put a 1.5 volt battery in it every time? I don't know. Okay, so now let's look at the interesting tricks you can play with batteries. Let's look at what happens when you connect them anode of one to cathode of the other. And let me point out to you that even if you didn't recognize you were doing this, you've done this many times. When you hook the butt end of one battery to the tail end of another, or I kind of said that the wrong way, the tip of one to the butt of the other, and you touch them, tip the butt, and slide them into the flashlight. You are doing what we call connecting them in series. And what you do when you connect them in series is you're combining their output power. So the term battery originally meant groups of cells. So really each individual battery, as the industry calls it, is a cell. When you hook 3 together, you make a battery. So your car battery in the good old days had cells. You could open the top of each cell up. And then collectively, there were 6 cells, each putting out 2 volts. And you made a 12-volt battery. Now, in a flashlight that takes 4 1.5-volt batteries, you're putting them in there so that they're connected so that the anode of one is connected to the cathode of the next. The anode of the next is connected to the cathode of the next. Now, sometimes what that means is you put them in upside down, one facing this way, one facing that way, and the current loops through them. Sometimes you put them in a straight line. But when you hook them in series, you always connect them so that the tip of one is touching the tail of the other. And I'm sure everybody knows what I mean when you slide those in to a battery connector. Now, what happens when you do that? Let's suppose I have this is one cell. It's got a copper on the left and zinc on the right, and I put my meter on and it reads 1.1 volts. So it must be a copper and zinc one like I made on the previous slide. If I connect them, now this might look ugly and it'll look a little better when we put a picture of batteries up here. I'm connecting the anode of one to the cathode of the next. But when you do that, you'll now get double the voltage. So when you hook 2 batteries together, you get double the voltage. When you hook 3 batteries together, you get triple the voltage. And these again have to be connected anode to cathode, anode to cathode, anode to cathode. Now let's stop and think of what that means. Let's suppose you have a flashlight that you have to slide 2 batteries into, or it won't work. You're connecting them in series. Typical batteries are 1.5 volts. You slid 2 batteries in. How many volts does it really take to run that flashlight? 3. So you're putting 3 volts of electricity in when you put the 2 batteries in. I used to have a big fancy boom box that took 8 batteries. 8 of them. Every 2 batteries was 3 volts. So that was 3 times 3. It took 9 volts to run my boom box that had 8 1.5 volt batteries. 8 connected in series is 8 times 1.5. 8, what am I saying? Did I say 8? Let me scratch that. 9 volts would be, 6 batteries. I can't even multiply in my head. 8 times 1.5 is 12. So if you need to put 8 batteries into a device, it's really running on 12 volts. If you need to put 6 batteries in, 6 times 1.5 is 9 volts. That would be a 9-volt system. Okay, now what does it mean to hook things in parallel? Now, to hook things in series, again, let me back up. You're hooking the anode of one to the cathode of the other, and you just continue this throughout. When you hook batteries in parallel, you hook the anode to the anode and the cathode to the cathode. That's parallel. Now, when you hook in parallel, you don't get any voltage advantage. Okay, so when I hook in parallel, the voltage is the same. Okay, I don't change my output voltage. What am I doing? Oh, the top is the series connection and the bottom is the parallel connection. Sorry. When I connect in parallel, instead of hooking the anode to the cathode, I'm hooking the anode to the anode and the cathode to the cathode. Now, you don't get any seeming benefit when you hook in parallel. Here's what I would say the benefits are. They're twofold. When you hook in parallel, you double the time that they can work. Each can work independent of the other. So when one goes dead, the other one still has its juice. So when you hook them in parallel, they would last twice as long. They wouldn't put out twice the voltage as they do in series, but they will last twice as long. Now, here's the more important thing. They put the same voltage out. And what does that mean? That's important if you want to use a battery power from one device in another device. Where is this most commonly done? In cars. If your car battery is dead and you ask somebody to jump your car battery, you connect the red thing to the red thing on their car and the black thing to the black thing on their car, meaning you connect the batteries in parallel. When you connect the batteries of the two cars in parallel, battery in car A is just acting exactly the same as the battery in car B. And that's what you want. You never put the red to the black and the black to the red. That would be connecting them in series. That ain't good. Matter of fact, one battery will probably overload and possibly explode. The bad one will start running in reverse, and the chemical reactions in them might occur so quickly that they might make gas. And when they make too much gas, the gas will explode the battery. Not good. So when you jump car batteries, you always connect them in parallel. When you connect them in parallel, they're giving the same output voltage. So battery A is literally replacing battery B in the other car. When you connect in series, you're doubling the voltage. And when you're doubling the voltage, when you do things like that, that's not what happens in the parallel case. Okay, so technically speaking, battery is an assembly of two or more cells. Individual flashlight batteries are really called cells. That's what, if you listen closely, that's what they call them. A battery, we use it interchangeably. A battery is a cell, but really batteries mean more than one. So in an automobile battery, it is truly a battery. If you can open it up, there are 6 cells in a car battery. Each cell outputs 2 volts. They connect them in series in the battery, and you've got a 12-volt car battery that has 6 individual cells connected in series. So battery materials vary widely, as I said. They're chosen. I talked about all these things, so I'm not going to say it again. Safety, cost, voltage, environment things, rechargeability things. This is what the battery industry strives for. Now, let's just look at what a typical battery looks like. In a typical battery, and you can cut one open and you will see, we call them dry cells because instead of having liquid in the middle, now they use like paste or jelly. There's not really liquid in the AA or AAA or D cells or C cells that we use. Cut one open for fun if you want, and you'll see there's like a jelly in the middle. So we call that a dry cell because it doesn't have the copper +2 floating around in water. So we don't put water in our batteries anymore. We typically use pastes and jelly kind of things. Then you have in this battery, it's not a copper battery. This is not the copper top battery. This one has a carbon or graphite cathode. So the battery I was showing before, instead of having this rod stuck down into it, would have had a copper rod. Now, if this was a Duracell, the copper top battery, that thing I'm sticking, that gray thing sticking there wouldn't be carbon, it would be copper. Now, the good old Ever-Ready batteries, the cheap ones, the silver ones, maybe you haven't even seen because I haven't seen them around in a long time, those had a carbon rod in the middle. The can is the cathode. The whole case on the outside is made out of zinc, and that's where the anode is on a typical battery. So then you connect them together. Did I not connect them together? I did. You connect from the top to the bottom. So the bottom of the battery is where electrons are lost. That's the negative anode. The top of the battery is where electrons are gained. That's the positive cathode. And so the electrons flow through the device, and we can harvest the electricity out of the device. So all these are these chemical reactions that I tried to show you on the previous slides. Now it just becomes a matter of what materials you pick to make the battery. Now again, the idea with a AA compared to a AAA is how much storage of juice and supply of long-lasting time you can deliver a certain voltage. So if you want to output a big volt or the same voltage, remember, as I said, the current that the battery uses is directly proportional to the voltage. So a device that wants triple the current needs triple the voltage. So you might want to use a D instead of a C, or a C instead of a AAA when you're doing things like that. Okay, so a primary cell is reversible and cannot be recharged, is irreversible. So the old cells you got to just throw out. A lot of them now are made so that you can reverse them. Okay, now what does it mean to be an alkaline battery? They have elements like sodium in them, in the first column, or ammonium in them. Okay, and I'm not so much caring about, I'm not even going to show you all those reactions, but they just take different terminals. So alkaline batteries use a different terminal. A car battery uses lead and sulfuric acid, so they're a little bit dangerous. There are 6, as I said, cells, and they're very rechargeable. That's why the auto industry loves the lead storage battery. This can be recharged real easily with your car alternator. So we love that. I don't care about the reactions. Don't worry about them. Now, one thing that is becoming really popular, though, is the fuel cell. And this is which burns hydrogen gas with oxygen from the air and makes water. So the output of this fuel cell is water vapor, which is very nice, but there's a good bit of electricity that comes out of a fuel cell. So believe me, we are really working hard to make fuel cell technology, and we want to do that so that we can improve the kinds of batteries that we get. Now, again, I know I'm blowing through these really quick. I'm probably not going to ask anything at all about these things at all anyways. I just kind of wanted to show them to you because they're very important. Certainly nothing at all to do with the chemical reactions and the voltages and all that stuff. I'm just showing you them because they're becoming more and more prevalent. Things like, of course, alkaline batteries, car batteries, certainly. And these fuel cells are really the wave of the future that we want to go to in order to get batteries that are safe for the environment, put out a lot of juice. All right, so another thing I do want to point out, though, that's closely tied to this is rusting. And rusting is called corrosion. And corrosion occurs because so much of our building material is iron, and unfortunately, iron reacts readily with oxygen in the air. And when iron reacts readily with oxygen in the air, it makes Fe2O3. And that is a brown, powdery substance, which you know as rust. So then, very simply, you take a piece of iron, oxygen begins to bombard it. And as the oxygen bombards it, it reacts on the surface of the iron. And it makes this red powdery stuff. Now guess what happens? More oxygen comes down, bumps the red powdery stuff out of the way, and finds fresh iron down inside the red powdery stuff and reacts and makes more powdery stuff. So more oxygen comes in, gets to the iron, makes more powdery stuff. And eventually the iron rusts through. So unfortunate for iron is the fact that iron oxide, this Fe2O3, is not does not coat the iron and protect it from oxygen. Oxygen can easily push past the powdery stuff and find fresh iron and then continue to rust the iron. So iron will do what we call rusting all the way through. Once some of the iron rusts, it's not protected by its rust. Other metals are protected by their rust. Now, what do I mean by that? Let's take a piece of aluminum next to a piece of iron. Oxygen from the air bombs the metals. When the oxygen from the air bombs the iron, it makes red flaky stuff, and more oxygen gets through and makes more red flaky stuff, and more oxygen gets through, makes more red flaky stuff, and then eventually rusts through. Now let's move to the aluminum piece. Oxygen attacks and reacts and makes aluminum oxide. But aluminum oxide is a coating that doesn't allow oxygen through. So the outer part of aluminum gets coated and won't allow any further reaction from oxygen, at least at first. If you get it wet and get salt on it, things like that, eventually, yes, it will. But aluminum coats over with an oxide that resists attack from oxygen. So aluminum will not rust through like iron. So that's the secret to why aluminum cans last a lot longer than iron cans, because the coating they get from oxygen is impervious or impermeable to oxygen attack, and oxygen can't get through it. Iron, on the other hand, makes this flaky stuff. More oxygen can get through, and it can continue to rust. Other metals have that same property, like aluminum. Magnesium. When magnesium is sitting around in the air, oxygen attacks. It attacks and makes magnesium oxide. But it coats the magnesium and doesn't let oxygen through anymore. So it won't rust through. So that's why certain metals, even though iron is the most popular metal because it's the cheapest and the most abundant, so we can work it very well. We've been working, bending it and shaping it and molding it for years. So we have invested a lot of time in using iron, but iron has the drawbacks of when it reacts with oxygen, it can't stop reacting with oxygen. It continues and continues and continues until it goes all the way through. So what kind of tricks do we do? Well, the simplest trick is to paint it. When you paint iron, you're putting a coating on the iron that now, as oxygens come, they bounce off. So painting iron protects the surface of it from attack from oxygen. So this is why Rust-Oleum was developed. Rust-Oleum was developed to protect iron from the attack of oxygen so that it won't rust through. I think if you stop and think about it, it would make sense. Now, when silver does this, it prefers to react with sulfur from the air, and it makes tarnish on silver that is, instead of having an oxide, it's a sulfide, interestingly. And copper, when it reacts, it makes a carbonate on its surface and turns it green. So the Statue of Liberty is a big green building that's covered with copper carbonate on its surface. Okay, quitting time. As I said, I went, if you tuned in a little late, I did make some adjustments on the scores. I added 5 points to everybody's test 2, part 2. I'm going to post some more, but I thought I'd wait a couple days to give us a breather. And then I'll see you on Wednesday. All right, so Peace out till then.